Ooh, an RC circuit. Now notice that this is a charging RC circuit. So this guy is not charged. As soon as you close that circuit there, the current's going to flow onto the plates of the capacitor, right? Flow off of that plate, right? Since it has to go through this resistor, that takes some time, right? So at first there's a large voltage, right, difference, and so it flows quickly, and later on there's less of a voltage difference, and so it flows more slowly. Okay, and this is looking at the voltage across the capacitor. Okay, now if you're looking at these things, the capacitor and the resistor are in series, right? So the voltage across the capacitor plus the voltage across the resistor has to add up to 12 volts because this is a voltage source. Okay, so basically you can draw a picture of what the resistor is, right? The voltage across the resistor is what they're asking you to draw, right? The variation of time of the voltage across the resistor is just going to be 12 minus the voltage over the capacitor. So just pay careful attention to it, draw a few dots, but figure out what, read what the graph is for the voltage across the capacitor, go 12 minus that. Like for example, here it's 2, right? So at this point we'd be at 10, right? Here it's at 4, right? At this point we'd be at 8, right? At 6 we'd be at 6, right? And then the mark scheme says, you got to be very careful about the crossing over at 6, right? Because that's when they're the same. Okay, so yes, okay. So let's look at the next one here. The time constant of this circuit is 22 seconds. State what is meant by the time constant, right? There's lots of things, right? The time constant is RC, right? That's the formula for it. So if we know the resistance and the capacitance, we can calculate it. But it's also, if we imagine this 12 volts here, right? Okay. It's also the time for it to get, say it's 22 seconds. It's right there, right? That's the time for it to get within 1 over E of the, or 36.8% of the 12 volts, right? So this is 0.368% of it. So you can just say that with words, right? And then calculate the resistance R. Well, if this is 22, right, and then this one is 4.5 picofarads. Oh, it's microfarads. If that's 4.5 times 10 to the minus 6, farads, then I think you can do the maths there, right? I do believe, right? Okay. All right, let's take a look at this next one here. Okay. A dielectric is now inserted between the plates of the fully charged capacitor. Notice that it's still connected to this thing, right? It's still connected to the voltage source, right? So state the effect, if any, of the potential difference across the capacitor. Well, it's attached to a 12-volt voltage source, right? It's still attached to it. And so even though we're changing the capacitance of that, we're going to basically double the capacitance. It's attached to a voltage source, and so I don't think the potential can change, right? The charge on one of the capacitor plates, right, is going to increase, right? And the reason for this is that the capacitance is the permittivity times, the area over the distance separating the plates. Now the distance doesn't change, the area doesn't change, right? But the permittivity is going to be bigger, right? So if this increases, then the capacitance increases, right? And then let's see, Q is CV, right? If the capacitance increases, then I think Q increases, right? There's only one mark though. That seems like it's a lot to say for one mark. I guess you just state it, right? All right, we can just say it. We don't have to back it up, right? Okay, so the permittivity of the dielectric material is twice that of a vacuum. Calculate the energy stored in the capacitor when it's fully charged. So previously the capacitance was a vacuum, right? So area over D, okay? Now the capacitance is twice that of a vacuum, right? So isn't it just twice, right? So the original capacitance is 4.5 microfarads, is 4.5 microfarads. Isn't the new capacitance 2 times that? I believe so, right? Is our new capacitance. So figure out the new capacitance, right? And then calculate the energy. Use energy is 1/2 CV squared, right? That's in section 11.3, right? And then it says the switch is now moved to position B. So we basically discharge the capacitor through the resistor. What happens to the energy? I'll let you come up with that answer, right? What happens to the energy of electric current flowing through a resistor? Yeah, don't overthink it.